Okay, so in this session, we're going to discuss solution of first-order differential equation using the Taylor's theorem. So in this lesson, you are expected to compute the approximating polynomial solution to an initial value problem using Taylor's theorem, compute the estimated error of the Taylor's expansion. Taylor's theorem is in elementary calculus is a very simple approach to approximate the solution to a first-order differential equation of this form. So you have dy over dx equals a function of x and y subject to the following initial conditions. So that when uh, x is equal to x sub o, the value of y is y sub o. Successive differentiation of y equals y of x, no, at x equals x sub o using the initial or the differential equation y prime equals f of xy will generate an approximating polynomial of degree n. So this is the Taylor's expansion that can approximate the solution to the differential equation. The estimated error would be this quantity, which is obtained by taking the next term. So this is n plus 1 derivative. And then your C here is any value between x and then the initial value x sub o. Okay, so let's have an example. Apply Taylor's theorem to solve the initial value problem. So y equals y squared plus x squared equal subject to the conditions that when x is equal to 0, the value of y equals 1. So with y within the interval from 0 to 0.5, now let us use an increment of 0.1 in this problem, and then we compare it with the true values of y at the end of the solution. So solving for the derivatives at x equals 0 and y equals 1, we have the following. Okay, so we know that this is equal to, y is equal to 1, so you have 1 here, or 1 squared. This will be 0 squared, so giving you y prime equals 1. And then derivative of y squared is 2y prime. Derivative of y squared is 2y, then since y is the dependent variable, so you have to multiply by y prime. Derivative of x squared is 2x, so we differentiate this implicitly. Now we substitute the values. This is equal to 1. This is also 1. Okay, this is 0. Okay, so we have 0 here. So 2 times 1 will 2 times 1 1. So that will be y double prime equals 2. Okay, now for y triple prime, okay, so derivative of this by product rule will be 2y, derivative of y prime is y double prime. And then copy y prime, derivative of 2y will be 2y, y prime. And then simplifying, we get 2 times y prime raised to the power 2. And then derivative of 2x is 2. Now substituting the values of y prime, which is 1, your y double prime is 2, y is 1, then we get the value of 6. And then for the fourth derivative, so derivative of this is 2y, y triple prime, plus copy, then derivative of 2y is 2y prime, plus 2 times 2, we get 4, y prime raised to 2 minus 1 will be y prime, then derivative of y prime is y double prime. Okay, or that is, we can combine these two terms to get 6y prime, and then substitute the values of y, which is 1, y triple prime is 6, y prime is 1, y double prime is 2, so we get 20 for the fourth derivative of y at x equals 0. And then for the fifth derivative, so this will be 2y, y to the fourth power, derivative of y triple prime, product rule, so copy y triple prime, then 2y prime, derivative of 2y. Product rule again, so 6y prime, triple prime, copy, then derivative of 6y prime is 6y double prime. So you should have here y double prime here. Okay. And then substitute the values. Okay. You should obtain 96. Okay. So that's choosing n equals 4. We obtain a fourth degree polynomial. No? So substituting in the Taylor's expansion, no? So we get the following. So this is your approximating solution to the given differential equation. Now, let's approximate the error. Okay, so using this quantity, so we use the fifth degree. Okay, so fifth degree, and then at n equals 4, so the next degree will be fifth degree at x equals 0.5. So we have the following. So this one, we obtained this from the previous slide, which is 96. The fifth derivative at x equals 0.5. So over 5 factorial, tapos your x is 0.5. This is your initial value. Okay, so this is the estimated error, no, 0.025. Now, if we try to, substitute, the values of x within 0 to 0.5 at 0.1, we obtain the values of the corresponding value for y. Okay, using the fourth degree, polynomial. So we obtain the following values at 0, 0.1, 0.2, 0.3, 0.4, 0.5. And this is the last column is represents the true values, no, for y at given values of x within 0 and 0.5 at an increment of 0.1. Okay, so as you can see, at 0.5 we have 1.89, that is quite close to 1.93. Now, if you want to increase the accuracy, you may increase the degree, the degree of the polynomial.